Okay, we are ready to start a new lecture. Short title is Ordinary Differential Equations, but this being a course on numerical methods, we're going to discretize ordinary differential equations. So most of you have either taken a course on differential equations or you're taking it parallel to this course. Technically, everything that you learned in that course we're not going to use. We're going to find a different way to solve the equations. That said, it's useful, of course, that you know what differential equations are about and that you know how to solve some of them analytically, but what we're going to do is solve them numerically. So I have skipped interpolation as a topic. I kind of always do it this time of the year, so we go directly to ordinary differential equations, and I'll get back to very short introductory lecture on how to do integration numerically, right? And then your numerical calculus is complete. You know how to discretize differential operators, and you will know how to integrate. Speaking of, the course project that is going to be posted is related to differential equations as well. It's basically one of the partial differential equations that is discretized. So what we're going to do is here is ordinary differential equations, and you're going to get sort of a sneak peek in how to discretize partial differential equations. Everybody knows what partial differential equations are? So let's first introduce ordinary differential equations, and we're going to mention some partial differential equations as well. So let's go with an example first. Let's assume that we have a container, and it's a cylindrical container, so we know its geometry and we can calculate it easily. And let's say that there's a water coming in here, okay, at a certain rate, and assume it's a function of time. So it's sort of like a periodical function of this rate coming in. Now, we also have a spout at the bottom, and there's water coming out, but at a different rate. And obviously, the size of this hole here is controlling how fast that happens. So we have a function that is basically we are in charge of, or somebody's in charge of, that we know, basically that estimates how much water comes in, and the control on the bottom is really gravity. Okay, so it depends on the height or the weight of the water column above it. Okay, and that is plus the geometry of this pipe down there. So that's what controls how fast the water will come out. Okay, so this is controlled by us, this is controlled by gravity, and there is an interplay between the two. Now, of course, the rate of things going out is dynamically changing with the height here. So if I accumulate more water, okay, then it's going to start going faster because there's a heavier column of water on top of it. And if it kind of starts emptying, then it's going to go slower. So this is dependent on the system itself. Okay, so we have to kind of constantly have that information, which is why it's extremely hard to come up with the solution to this by hand. Okay, so the change of the mass here is the standard mass conservation. So this is the most classical physical law that you get equations or that you solve the problems with. We already had it in our linear equations where we had that those tanks also that were connecting to each other, and there was a flux in between them. And basically we use this, well, if we are going to have this at steady state, this flow through, then whatever comes in has to be the same as what comes out. Here, there's another formulation of that same principle, is maybe you don't have a steady state so that everything that comes in is going out. And if you don't, then the difference is basically the change of the mass within this tank. Okay, so change of the mass within a system is equal to the difference between what comes in minus what comes out. And that's essentially the more general version of the mass conservation in this tank. So the change in mass in time in general is the change in mass of what comes in minus what comes out. And we can also relate, of course, the mass of what's happening here to the height, okay, because we know all of the other. So if I know what my area of this tank is, then area of tank is constant, my density is constant. So if I take the derivative of that, I can basically take those scalars outside and just have dH dt instead of dm dt. Everybody sees what happened here? Okay. And then I put in the functions that I have here. So in this particular example, this equation has dH dt here, and it's the square root of h over here, and also cosine of t. Finding h as a function of t is obviously not trivial from this nonlinear functions here. Okay. And this is basically where we need numerical methods. So you've learned how to solve in your differential equations class quite a number of classes of differential equations by hand. Okay. And that's useful. A lot of equations in practice fall into that group, and if you can find an analytical solution, that is always the fastest and the best thing you can do. However, that's about, well, I'd say 5% tops of the equations that we need to solve. All others come like this, and there's no changing. Nature is nature, so this ain't gonna change, okay? So, and this maybe we are in charge of changing, so we can maybe change this to a bit different function. Maybe you're in charge, maybe you're not in charge. That depends on the system you're in. Who knows where is this water coming from? If this is a collection of water from an entire small town, okay? No, you don't have a function that describes it. You have data, okay? And you can maybe fit that data and create yourself a function, but it's not going to be a pretty one necessarily, unless you really go for linear, in which case you might make some gross mistakes. So overall, we sometimes have control, but often we actually get equations that they are what they are, and you don't want to introduce more error by changing or linearizing the problem or something of that sort. So we need a numerical way to solve this. So just to review quickly, differential equations, I can have two types of problems. Time-dependent problems will be so-called initial value problems, because I have to know what's happening at time t is equal to 0, and then I solve from there. Okay. So in this particular problem, we will specify mass at the beginning of the time that we want to solve for, and then go from there. It could also be a boundary value problem. If you remember that heated rod, okay, that had temperatures at the boundaries, and we were actually looking for a steady state solution to that problem. So it's not time dependent, it's really just a boundary value problem where you have specified functions on the boundaries and you are solving in between those boundaries. So that was our discretization of the temperature for the rod. And then we also say order of the differential equation. It really refers to the order of derivatives that show up. So you could have dy dx, in which case only, in which case this is a first order equation. And we are, for the most part, going to deal with these. And second order equation is d squared y dx squared is equal to 4, so I have a second order derivative. This can be basically, I can define dy dx as a new function, z, okay? And I can actually, there's a way to transform this in a system of linear equations, of first order equations, right? So basically, a lot of, and we're going to get to this, so a lot of methods that we just know for solving these equations we can apply to systems of ODEs. This is an example of a partial differential equation. Another example you will have in your course project. So this is basically second order with respect to x. So this is a partial derivative. And something weird happens to my um, to my as Microsoft changes versions, weird things happen to my equations that are in there. This is supposed to be partial derivative, and it has been. I don't know what happened here. So it went back to D. So this is delta and D are similar letters. Delta is really just a D in the Greek alphabet, but I don't know how did this change. So this is a partial derivative with respect to x, and my function p is p of xy. So it has two derivatives. All right. So let's introduce the first class of problems that we're going to attempt here. It's so-called initial value problems, and we're going to, the entire, there's a number of methods here that we're going to use, and they're all called Runge-Kutta methods, though some of them will still have separate names for different varieties of the methods. So if I have equation of the form dy dx is f of xy, and I went to a general notation, we had dh dt is a function of t and h. Okay, that was our example at the very beginning, right here. So I had dh dt is a function of t and h is a function of t. In this case, I have dy dx, so y is a function of x, and I have some mixture of x and derivatives, and y on this other side. The derivative is here. Okay. So the simplest way to solve this, we're now looking for a solution. So this is a function of x. So what we typically do is we're going to discretize our little world of x's on some interval. Okay? And we're going to now look for y as a function of x on that interval. Okay? So basically I'm going to have x1, x2, x3, x4, and so forth. I'm going to discretize, right? And I'm looking for y1, y2, y3, and so forth that correspond to those x's that will give me function y. That's essentially what we're looking for. So the simplest thing is to start from a value that you know, and after that, h is basically my spacing in my discretization. So I'm going to say, okay, my new value of y, or y and the next point, is what I had at the previous point plus slope times h. Okay, and this really comes from, let's see, so basically I have my xi and xi plus 1. Okay, so those are two, and this is my interval where I'm solving. So somewhere in the middle, starting from this point, assuming that I know I came up with yi, my next one will be simply, okay, yi plus 1 is this old value plus this slope times distance h. Okay, and this is simply from this triangle here. That's assuming what the slope is. So what's a good estimate for slope? It's, what is this slope? It's drawn here as a slope. So what is it in terms of function y? Derivative. So this slope is actually dy dx at xi. Yes? dy dx at xi is a function of xi yi. Yes? That's what we're solving actually. So basically this slope is this, evaluated at point xi. So that's pretty simple then, right? I know what slope is. So basically my slope phi, you will hear me call this phi or phi, so it's a Greek letter, f of xi yi. And that's it, that's our method. So my yi plus 1 is yi plus f of xi yi h. and h is the spacing that I came up with in between points. And the only thing that I need to know a starting point. I need a start from somewhere, some start of the interval where I need actually a value, initial value. And that's it. That's the method. If you see this, can you program it? You need to know function f. Okay, that's given. So you program a little function that evaluates f at xi and yi. And the rest is a for loop and quite literally one line of code. Easy? Does everybody see it? You're going to get to see it anyway. We're going to do it. so this is called so-called Euler's method. Okay. So essentially I need a first derivative, which is given by the problem because this is what I'm solving to begin with. Okay. And I basically, I need a step size h that I determine myself. So basically this is how it works. Let's say that I'm solving on 0 to 4. I start with some starting point, and then I decide on discretization. So here, discretization is h is equal to 0.5. Okay, so I start with the discretization, and then my value at this point, okay, is this value plus this slope, which is f of xi, yi here, times this h. So that's what takes me here. Now, obviously, in this particular case, this is not, doesn't look very good, right? So, how do you think this improves? What's one thing that I can do to improve how close this solution is to the true solution? Is this step size, are you happy with the step size h? So that's something, I kind of go too far. It starts really well, right? And then it shoots up too far. So obviously my h should be smaller so I don't make such gross approximations for too long of a step, right? So basically if I did half h, if my h was 0.25, I wouldn't be making such a big mistake. Right? It would take me here, and that's fine, and then I would recalibrate, reevaluate my slope, and go from there. Because at every point I reevaluate my slope. One thing that you notice is that if I make a great mistake, or like quite a large mistake, this is my error, right? If my error is large here, well, I can make up some later, but basically it kind of gets worse as I go on from there because I accumulate error. If I made a large error at the first step, it stays in all of the other steps that come afterwards. Okay? And that can be a problem. So let's just look at error analysis and how does one look at the error here. So my yi plus 1 is equal to yi. So basically, if I had my function y of x, okay, this would be y of xi plus 1, and it's equal to y of xi plus, and this is dy dx. So this is Taylor series. If there's any calculus thing that we're using all over again, it's Taylor series formula. So this is again y of xi plus 1, this is y of xi, and this is dy dx at xi. Okay? So this would be Taylor series, and then it keeps going actually in terms of the order. So our Euler's method is really, you kill the higher order terms in Taylor series, and that's where it came from. Okay. What other methods can be proven to review for the test? What other method can be derived from Taylor series in root finding? Newton's method. and we actually did that in class, if I recall correctly. So there's a way to approximate things and find the method, Newton's method, or reformulate it from Taylor series. So Taylor series is very useful thing. So basically I have, so if this is my method, okay, then this is the error I'm making. Okay, at each step I basically don't compute this part because it's higher order, it's expensive for me to compute. So when you truncate, you have a truncation error here, right? Truncation error is the error that we get when we approximate formulas and we simply cut off certain part of the formula, right? So this is my truncation error, okay? And we call that local truncation error because it happens at every point. And then I also know that that's the error that I keep propagating because it accumulates. If I had it at my y1, I'm going to carry it over to computing y2. And at step y2, I'm going to make error again. Okay? So these things sum up as we go. Okay? So this is a truncation error. And then what we really, we look at it, so this is this term in this entire equation. This term is sort of the dominant term over all of the others. So basically our error is approximated as h squared. Because if h is a small number, then h squared, let's say that is 0.01, h squared is much bigger than h cubed. Okay? So all of these other terms are typically small, and this is the dominant, this part is the dominant part. Now, good news is that this error, as h goes down, so does the error, right? If my h goes from 0.1 to 0.01, obviously this gets much smaller. So that's great. So this is basically what we would get. This is that suggestion with h is 0.25. I would actually get much better. So I wouldn't make such a big mistake here, and then I would get much closer to my true solution. And if I went further to h is 0.02 or something like that, I would get very close to the actual solution. So reducing step size reduces the error. Now, let's just see all of these errors as they put up. So basically we have this local truncation error, which comes from basically chopping down Taylor series. And I also have this, what we call propagation truncation. So because I made an error in the first step, that error propagates forward because I'm starting from a wrong value. Here, I'm starting from this value, not the true value. Okay? So because I'm starting from this value, at this step, I'm making a truncation error again, but I also have an error from the previous step, and that we call propagation error. So it kind of piles up by the end. So all those together give me global truncation, which is combination of both local and propagation error. Okay, let's stop talking. Let's actually start programming. So let's assume that I have the following problem again. This is my Euler's method, and my dy dx is given by this equation here. Now, if you took differential equations, and almost even if you didn't, there's no y in here. So this is actually simple to integrate. Yes. So we do have analytical solution. Here it is. Again, I'm not asking you to come up with it, but this is my analytical solution. So I have y of 0 is equal to 1, and this is the problem I'm solving. Let's solve this using Euler's method and compare to our analytical solution. So we typically start from simple stuff I can compare to analytical solution just to see how well we do. So let's solve this on 0 to 4. So this is my interval. And let's use first step size h, but you want to program it in a way that you can change h easily. Okay. But before you head into programming, let's just compute this by hand. So If my first starting point x1 is 0 and y1 is 1, compute what is y2, and also find the relative error. And I had the solution there that I quickly removed. So let me know what you get. So what did you get as y2? If my h is 0.5, my x2 is 0 plus h, right? This x1 plus h. So my x2 is 0.5. Okay. So my y2, according to this formula, is y1, which is 1, plus f of xi yi, which I have to, this is my function. This is the problem I'm solving, right? So this is my f of xy. So for 0, well, that's easy to compute. It's 8.5. Okay? Plus 8.5 times h. Did everybody compute that? What do you get as y2? So now my program just needs to automate that in a nice little loop, right? So we can change h to whatever. So program Euler method, I would create a function first that takes your h, it takes your start x1, it takes a value at that start, so these are your initial conditions, and it gives an interval end, yes?
So it's given that y is 0 is 1. So are we trying to solve for y x? We're solving for x, like the part of x to y2, right?
Yes. So you're given this point, okay? Y of 0 is 1. Okay? And then you're trying to find the rest of the function. So you're trying to, you kind of discretize, and you try to find value of this function at these discretized points. And at this point, you're just going to what you computed already. In this case, it's just the initial condition. And plus slope times this step h. And that gives you this. This is approximation of this value. This is the true value. This is the approximation. And my h, when my h was larger, this was my true value, and this was my h. This was my approximation, so the error was larger. You're making an error, but as h gets smaller, you're getting closer and closer. So basically start from one value, and you're giving yourself, you're looking for this function at a finite set of points that are equally spaced. And that gives you this function. Does that answer your question?
Well, I mean, so my question was so you go back to the other slide. You have to plug in 1 for the yi.
Yes. So
0.5 to the dy dx, and then multiply that by h. Is that how you get y2?
right. So I get y2 is y1, which is 1, right?
Okay.
Plus h, which in this case is 0.5, times f of x1, y1, which in this case is 0, 1. This is my function f. It's actually just function of x. It's not a function of y. Or in mathematical lingo, it's a trivial function of y. It doesn't depend on y. So it's just really f of 0, which is 8.5 in this case anyway, right? So in general case, this is going to be a function of y. But I chose this case so you can quickly integrate and give yourself an analytical solution to compare it. Okay? So this is your program should kind of take in any h, whichever you'd like, and then you discretize this. You have interval start, which is x1, and in this case, this is going to be 0 to 4, right? So I'm just going to give myself however many points with this distance in between h. We know how to create equally distant points, right? And then you have a for loop that goes in here. And you want to give back these vectors x. X is simply discretization of your interval. In this case, it's going to be, you're going to run it with 0, 4. And y is basically a set of values that you found at those points. And you want to compare this solution for 0.5, 0.1, and 0.05, an analytical solution. This is how it looks like, by the way. This is what you're going for. So analytical solution is here. And you can see for 3 different step sizes how you get closer. Okay? All right. I'm going to stop the video, and you can... Or rather, I'm just actually, this is useful to have, right? Then I'm just going to stop, and I'm going to walk around.